Kia ora koutou, welcome back for lesson 9. Today we'll talk about state changes, Enthalpy change, and be introduced to entropy. Just a reminder from last year, temperature is directly related to the average kinetic energy of our particles in a substance, so they're directly proportional to each other. So by increasing the temperature of a system, we are increasing the average kinetic energy of the particles within that system. A reminder of the phase changes. We have our three phases. We have solids, liquids, and gases. Heat energy is either absorbed or released for a substance to undergo a phase change. For example, we have the heat curve relating to the heating up of water. So reading off the graph, you can see we have our temperature here. On the y-axis, we have our time, and you can see we're starting at minus 20 degrees. So of course we'll have solid ice. We have our solid phase, our liquid phase, and our gaseous phase. So here in our slope sections, it indicates that our particles are gaining kinetic energy from the surroundings. The temperature is a measure of that average kinetic energy. And we can see here on the left, we can see that in these slope sections, we are getting an increase in temperature. However, we also have these flat sections, which actually show that the water is not gaining temperature. The energy is instead being absorbed. This is because that energy is being used to break the intermolecular bonds between our water molecules to help them to change phase. So when we're in that solid state at 1, the flat section instead at 0 degrees or at the melting point, the energy is being used to break apart those water molecules and allow them to slide next to each other, such as in a liquid. And then of course here again, we have no longer an increase in temperature because the energy is instead being used to evaporate the liquid water and free these gas molecules by breaking those intermolecular forces between them. And there are our two flat sections. Today we're also going to talk about latent heat or enthalpy. The first of these is enthalpy of fusion, referring to the amount of energy we need to change 1 mole of a solid to a liquid. So I have an example here, and we use this symbol, delta FUSH, equaling 6 kilojoules per mole. That indicates to us that in order to undergo this process, melting ice, we need 6 kilojoules absorbed to change that 1 mole of ice to liquid water. Enthalpy of vaporization is similar. It's the amount of energy that we are required to put in the system to change a mole of a substance from a liquid to a gas at that liquid's boiling point. So another easy example is we have our liquid water becoming gaseous water or water vapor, and we use the symbol enthalpy of vaporization being 40.7 kilojoules per mole. So at 100 degrees, that means 40.7 kilojoules must be absorbed to change 1 mole of liquid water to water vapor. And finally, we have enthalpy of sublimation, referring to the amount of energy required to change a mole of a substance from a solid to a gas. So in sublimation, we have a process where the liquid phase is skipped. We're going straight from the solid to a gas. An example of this is iodine crystals. Energy must be absorbed to change a mole of liquid water to water vapor. And it is represented similar to the others with delta and then S, U, B for sublimation, and then your H, like that. So that refers to the enthalpy of sublimation. Next, we're going to talk about entropy, which is a new idea this year. So entropy refers to the degree of disorder in a system. In a system such as a gas phase, we are going to have a high amount of entropy or a high amount of disorder or randomness. Then as you change phase towards a solid, you actually have low entropy or low disorder. And I'll elaborate on this shortly. Consider a bedroom. When it's tidy, we say it's in a state of low entropy. or low disorder. However, as it gets messier and messier, the entropy increases to a state of high entropy. We use the symbol S to denote entropy. So, of course, change in entropy, which is a value that we're going to be very interested in the coming weeks, is delta S equal to the final entropy minus the initial entropy. So just as a little bit of practice, we're going to take liquid water and solid water. So of course, liquid water is in a higher state of entropy than solid water. If you go back to the tidy room analogy, you can imagine the particles in solid water are much more organized, they're much more ordered than that in the liquid water, which are allowed to slide past each other. So as a result, we have much higher entropy on this side and lower entropy on this side. And going back to our equation, delta S is entropy final minus entropy initial. So our final entropy is low minus our high entropy initially, meaning that overall, our value for delta S, or our change in entropy, is going to be negative. Take the opportunity to consider these questions about the entropy of fusion, sublimation, and vaporization, our heat curve, and as well as our entropy change.